Welcome to the SOFiSTiK online documentation. In this part of our composite bridge tutorial, we will show how to do the structural analysis for our bridge system. You will start by calculating the construction process, and for this purpose I would like first to introduce it. As you can see, in the first construction stage we have only the structural steel parts active and they are subjected to their own self-weight. Then we pour the concrete in the span sections. You can see, then we get a corresponding deflection of the steel. Then the concrete in the span hardens. You can see now the parts where we have poured the concrete. Then we have a step where the concrete creeps and shrinks. Then we pour concrete in the still missing parts around the inner support. This concrete hardens and gets active, and then we have some additional dead loads on the structure that lead to some further deflections. And then finally we have some further creep steps, first now here until traffic opening and then until the end of the bridge life cycle. Now I will show you how to define this construction process in the analysis. So for this purpose we insert the task construction stages, open it, and you can see that the first step is here to define the construction stages. So we have some predefined stages already available. However, I will add some further ones and modify some of the already available ones. So here I will introduce stage numbers 19, 20, 25, 29, 30, 40, 45, and 46. Okay, now we will define the titles. So what are the individual stages about? So okay, first is about the self-weight of the steel structure. I will keep that. The next one is about pouring the concrete in the spans. Then the next step will be used to show the hardening of the concrete. Then we have a creep step, get the effects of creep and shrinkage in between the construction stages. Then in the next stage we will pour the concrete around the inner support. Then this concrete hardens. Then in the next stage we put the additional dead loads on the structure, and then we have some further creep steps. So I would like to distinguish here also this already defined creep step in creep that happens before the traffic opening, which I will here call creep T1, and creep and shrinkage happening after the traffic opening, which I will denote as creep T infinity, so until the end of the bridge life cycle. Now we have to make sure that we have the correct types defined for these stages. So the first one is okay, self-weight of action G1. Then second one will also be G1 self-weight. Then we have a construction stage where the concrete hardens but no loads are applied. Then we have C1 creep until traffic opening. That's already fine here. Next, I will put here again self-weight for pouring the concrete. Then we have a construction stage when the concrete hardens. Then the additional dead load I will put in action G2. And then we have once again C1 creep until traffic opening and C2 creep after traffic opening. That's fine. Final point to do in this tab is to now set the duration of the creep intervals. So for this, for the creep intervals in the construction process, I will keep this 28 days here, but for the creep of the traffic opening until the end of the bridge life cycle, I will set 30,000 days. Then I have to set the climate conditions. So here I would rather like to have 80% relative humidity instead of 70. I can set the temperature to 20 degrees are fine for me. And here in the last column, I can set the creep steps for the creep stages during and immediately after the construction process. That are rather short, here 28 days. I will keep one step, but for the interval for the creep after the traffic opening until the end of the bridge life cycle, that is rather long, I will set 3 creep steps. The reason to divide a creep interval in several steps can shortly be summarized as follows. In a statically indeterminate structure, creep and shrinkage leads to a change in the internal forces, leading to a change of the stress in the concrete slab. The change in the stress in the concrete slab in turn affects the development of creep. In SOFiSTiK, this overall effect is resolved by dividing the creep interval in several discrete time steps, as we have done now. Having the stages defined, we now can go to the Groups tab and define the properties for the individual groups. And most important, define when they should start to be active in the system. So for that, I would like to shortly recall which groups we have in the system. So in group 1 and 0, we have the beam elements and the bearings and couplings. So basically everything that I would like to activate already in the first construction stage. Please note that the information if these beam elements here have a concrete slab already or not will be guided by the construction stage assignment in the cross section itself. So we do not have to care about this here. So all this here, group 1 and 2, I will assign to construction stage 10 later on. Okay, then what about the other groups? Now, as you might remember, group 2 is are the area elements in the span. So they will be active when the concrete in the span is hardened. So that is construction stage 20. And of course, then we will also later on do the concreting around the inner supports. So there we would like to activate the area elements in group 3 in construction stage 30. Okay, let's do this. So group 0, first activation, construction stage 10, that's fine. Same for the group 1. Okay, now group 2. I would like to have this in construction stage 20, and group 3 should be first activated in construction stage 30. Okay, they all should be active until infinite. And in the column concrete age, we can set which age the concrete elements already have when we activate them in the system. Here I will set 1 day to really cover the complete shrinkage effects in the concrete. Important in our system is also this column here. This is about the application of the concrete self-weight in the beam elements. A short reminder. When we did define the cross-sections for the main girders, we assigned construction stages to the cross-section elements. So for the span cross-section, for example, stiffness of the steel is already activated in construction stage 10, but the concrete elements then come in construction stage 20. Now, of course, the concrete weight acts on the pure steel section, so we want to apply the concrete weight before the concrete stiffness gets active. And for this, we can use this option C2 concrete load from -1. This means the concrete self-weight in the beam elements will get activated one construction stage before the stiffness of the concrete elements. So we will have concreting loads in the span, for example, in construction stage 20 minus 1, which equals 19. Now, as you know from modeling the system, we are activating beam elements which represent the complete composite section, including the concrete slab, and we also have area elements which also represent the concrete slab. Now you might already wonder if we do not account for the slab twice in our analysis. As you might remember, we handled this topic for the self-weight by assigning the area elements a concrete material with zero weight. The topic of the stiffness we will treat now. The idea is, because we focus here on the design of the main girders, we need the area elements only to connect the girders and to apply and distribute loads in cross direction. Therefore, we will switch the stiffness of the area elements in longitudinal direction off. So the stiffness of the concrete in longitudinal direction will be represented only by the beam elements. For this purpose, we use stiffness modifiers for area elements called QUEA and QEMX. The first applies to the membrane stiffness of the area elements and the second to the bending stiffness in local x direction of the element. We set both to 1% for the groups containing area elements. Please also check here if the local x direction of the structural areas is oriented in longitudinal direction of the bridge. So that's it for the group definition. Now we can define additional loads that should be applied in construction stages. As you might remember, we want to have some additional dead load that we also already defined in construction stage 40. So now to get this, I first select a load case to get the loads. As you remember, in load case 1 we defined this additional dead load, so I choose this load case here, and of course I have to set when I would like to activate this load, and this will be done in construction stage 40 that I created for this purpose. And the loads shall be active until infinite, so not to be removed somewhere in the construction process, and yeah, factor should be 1. Then we can run the construction process. So run OK. And we take a look at the results. So the sum of effects from the construction process here are stored in load cases with number 4000 upwards. So you can see 4010 is what happens in construction stage 10, then 4019 is what happens up to construction stage 19, and so on. So here we see we get some loads from the wet concrete, the concrete hardens, we have some creep, some concreting in the at the support, then the this concrete hardens, we have the additional dead loads, and then further creep and shrinkage. Okay, looks like what we would like to have. Now, second point here, you also see we have this load cases from number 5000 upwards. These now are the difference load cases, so they carry just the effects that happen in the individual construction stage. So here now we can also take a look at the stress development during this construction process. So we go into the result view to design cross sections, stresses of AQB, in beam elements, and select reinforcement steel stress and axial material stress in the section. And we will start from construction stage 10, and I would like to select the representative section somewhere in the span. Okay, now you can see here we only have stresses from the loads due to the sulfate of the steel. Then we pour concrete, then the concrete hardens, and now we have the first creep step in the section. And as you can see, so this is something that is calculated with linear elastic material behavior. So as expected, we get more compression in the top flange, now here from the shrinkage tension in the concrete. However, as you can see, we do not get compression stress in the reinforcement. And the reason for that is that we haven't requested this now. To get this effect, we have to make a small adjustment in the construction stage manager. However, this is something that cannot be done in the graphical task. Therefore, I will convert this to a user task, so basically a text input. Now, this text input here basically represents what we have defined in the graphical user interface. So here the table with the construction stages, construction stage numbers, the titles, the types, then table with the groups, so the groups and their different properties. Here you might also recognize some things from the user interface. And we have the table of loads. Now I would like to add here small text input and rerun the calculation. And as you can see now, yeah, as expected, we now get compression stress not only in the structural steel at the top flange, but also in the reinforcements. Okay, then we can click through the construction process here, some further loads from the concreting, adhesion supports, then this concrete parts hardens, then we have the additional dead load, and then some further creep and shrinkage. Okay, now I will also make a second adjustment. The point is that we would like to do our design checks later on the basis of design elements, which we have already designed and which we used to define the structural members that we want to design, respectively verify. But to get all the relevant information from the construction process onto the design element, we have to explicitly request this. So for this purpose, I here modify the control option to this value DSLN, which means put really every relevant thing, basically also the primary effects, onto the design element. Okay, I rerun this. Then we have the construction process finished and can proceed with the next steps of the analysis. So we have calculated the construction process, but of course we have some further loads that we want to analyze. So for example, the temperature loads and the settlements that we defined. And for this purpose, I will insert a new task, linear analysis. I open it, and as you can see, we have a lot of load cases available there, but of course we do not want to have all of them, but only those that are relevant to us. So I select the settlement loads and all the temperature loads, and then I can run the analysis and use graphic to take a look at the results. I go to results, beam elements, forces. So I'm interested in the bending moment. That looks fine. Same for the temperature. Now, important, as you might still have present, we reduced the stiffness of the area elements in longitudinal direction of the bridge to have the stiffness of the concrete slab not considered twice in the system. The settings that we made here will be taken also here in the linear analysis task. You also can see in the report that you get the corresponding notification. However, now in our case that's fine because we also in the linear analysis want to have this reduction of the area element stiffness. You also can check it. So if we have longitudinal or axial stresses in the area elements, so axial direction of the bridge, therefore I go to forces, membrane forces, NXX. Okay, that's close to 0, that's fine. Same for the bending moment, MXX. Okay, I will also shortly check the X direction to be 100% sure. Yeah, okay, worked as it should. So temperature and settlement loads accomplished. Now, as next step, we can go to the traffic loads. And for this, we will use the traffic loader task that I insert for this purpose. The traffic loader calculates results, for example, internal forces of beam and area elements for traffic loads. And this is done by evaluating influence lines and finding for each element the decisive load position. For this purpose, we have to define the traffic loads to be investigated and the positions where they can be placed on the bridge stack. Please note that the evaluation of the influence lines needs information about the system's stiffness matrices, which are taken from a previous linear analysis of the system. So, when using the traffic loader, please make sure you have done a linear analysis with the correct group and stiffness settings before. Okay, now enough background. Let's start with the definition of the traffic loads. So open the traffic loader, and as you can see, we first have to define the limits of the bridge deck and the carriageway in reference to the bridge axis. So here I will place -2.5 for the position of the curbstone left and 2.5 for the curbstone right. And the bridge deck left is at -3 meters and +3 meters on the right side. Okay, based on the dimensions of the carriageway, several lanes are created in different alignments. So in the center, here lane 1, then on the right, lane 10, for example, and on the left, lane 20, and also lane 0, which basically is the whole superstructure width. These lanes we will use later on to define possible load positions on the bridge deck. But of course, first we have to define the traffic loads that we want to use. So this is done in the next tab. Here I create a load model LM1 from Eurocode with axle load of 300 kilonewton. Okay, next we go to the calculation tab and first define which results we want to have. So in this tutorial we are primarily interested in beam forces. As you can see, these are already available here. If you need further results, you can of course add a line and select them. Next we need to define how we want to treat the load distribution in transverse direction. We have defined area, respectively shell elements, for this purpose, so we can use the option to evaluate transverse influence lines on these shell elements. Here I will use the number of 9 interpolation points for this transverse influence line, which is the most accurate option. Okay, then we can proceed and define load positions in cross direction by defining load groups. So I add a new load group, and this first load group is about the results for the LM1 tandem system loads. So I will give it a corresponding title. You can also see this load group has a base load case number for the load cases where we will find the results. For example, the results for this load group will be stored in load case 100 plus an offset for the result item, and these offsets are defined here in the calculation tab. So for example, for the maximum bending moment My for this tandem system loads, I will find the results in load case 109 for the minimum and 10 for the maximum. These load cases are also assigned to an action that we will use later to reference them in the superposition for the design combinations. So here I choose the previously defined action GRT. Okay, now there are of course several possibilities how to position the tandem system on the bridge stack, and this topic is handled in the so-called cases. So each load group can have several cases. Here I will create a new case, and each base basically represents a possible load setting in cross direction. So for example, here in this case, I will define a positioning of the tandem system aligned on the right. So in lane 10, I have to select the load model that I would like to use. So LM1. And of course, we do not want to have all LM1 loads, but only the tandem system now. This you can do here in this group tab. So I only want to have LM1 tandem system, and you can see now this is the only load pattern that is applied in lane 10. Okay, now we create a second case for aligning the tandem system on the left. So as before, alignment, load model, and load group. Okay, next we treat the UDL loads. For this we create a new load group, define a title, and select the corresponding action defined for this purpose. And now, in the same way as previously, place the UDL loads in right and left alignment. Furthermore, we also want to have loads on the remaining area beneath the carriageway. For this, we create a further case, select alignment superstructure width, and choose to place the residual load here. You can see how it is now applied on the areas beneath the carriageway. Okay, now because these cases are treated as mutually exclusive, what is still missing in our setting is the possibility that the carriageway and the remaining area beneath are loaded at the same time. To get this, we can create combinations here on the right. So first I will create a new combination and combine case 1 with case 3, and create a second combination and combine case 2 with case 3. And now important is to make sure that these combinations are treated mutually exclusive. Otherwise we would have the loading twice on the structure. For this purpose, we place them in the same alternative load group here. So for example, A0. Okay, now we have everything defined and can run the traffic loader. Okay, then we will take a look at the created results. So I go to graphic and select results for beam elements, forces, for example, bending moment My. And now, as you can see, for example, as noted previously, I will get the minimum bending moment My due to the tandem system in this load case 109. Okay, then next load case, maximum bending moment My due to the tandem system. And for example, now for the UDL loads, we have the same thing in load case 209 and 210. Okay, as you can see, we have the loads available on the beam elements, but as I would like to show you, we do not have them available on the design elements yet. So to get this result load cases from the traffic loader to the design elements, we have to map them from the beams on the design elements, and I will show you how to do this. So we go back to the SSD, insert a task, text editor, I will name this map traffic loader results to these design elements. Open it, and now we'll paste the necessary input. You also can copy this for the projects. So what I basically do here is calling the module decreator that's responsible for the design elements and telling the decreator to map the results from the beam elements of the load cases 101 to 112 in steps of 1, so all these load cases in this range, to the design elements, and the same for load cases 201 to 212. Yeah, and basically that's it. I will run this, and we can now take a look at the design elements. So as you can see now, these load cases are available also for the design element. Okay, so that's it about the analysis of the system. Next, we will do the superpositioning for the design combinations. So see you in the next video.